Section 4.2, the mean value theorem. The mean value theorem is something that is going to be used to develop future results in this class, but also has applications that we can use directly with this theorem. So first we're going to talk about something called Rolle's theorem, which is a subset of the mean value theorem. And you're not going to have any problems with Rolle's theorem, but you will see it referred to, so I want you to know what it is. So again, calculus is a lot about taking language and notation and figuring out what it means. And often, most of the time, drawing a picture will help to decipher some of the language and notation. So Rolle's theorem says, let f be continuous on a closed interval AB and differentiable on the open interval AB with f of A equal to f of B. So these are the conditions that have to be met for us to use Rolle's theorem. So let's look at what that means. So we have a function, I need a function between A and B, the closed interval AB, that needs to be continuous, so it can't have any holes in it, it can't have an asymptote or a vertical asymptote, it can't have a break in it. So we need to draw a continuous function, and it also needs to be differentiable, which it means it can't have any sharp edges or vertical asymptotes, or not asymptotes, but a vertical slope. And so any function that I draw in here, it can be really simple. I could just do this, or I could do something wild and crazy and go up and down, or I can just be sort of middle of the road and draw something that looks like that. So that's a continuous and differentiable function on that interval, and f of A needs to be equal to f of B. So in Rolle's theorem, this is the main difference between Rolle's theorem and the mean value theorem, is that Rolle's theorem has to have these endpoints at the same height. So this height and this height, f of A is equal to f of B. There's at least one point C in AB, so some x value C within AB, such that f prime of C is equal to 0. All right, and now what that's going to come from, and the part of the mean value theorem that we're going to extend to, is what's happening is we're going to connect these endpoints and the secant line between these endpoints. And Rolle's theorem says that there will be some value of C where the slope is equal to 0, or the slope is the same as the slope of the secant line. So if one thing that we can do is take a ruler or a pencil. I don't have a ruler right with me, but we can take a ruler or a pencil or a piece of paper, and we can slide it with that same slope of 0, slide it until we hit a part on our function that has that same slope of 0. So if I look right here, and we know that that represents a critical value, all right, for our function, so it's either high point or low point, all right, but that's going to have a slope of 0. And if I slide my piece of paper up right there, I get a slope of 0. So that's what Rolle's theorem is saying, that there is at least one value of C. In this case, we have C1 and C2. We have two places where that f prime of C, the derivative of the function at C, is equal to 0. The slope of the function at C is equal to 0. We're going to extend this thought to the mean value theorem, and the mean value theorem actually encompasses Rolle's theorem, so we don't need Rolle's theorem if we understand the mean value theorem. So the mean value theorem, let's look at the language. If f is continuous on the closed interval AB and differentiable on the open interval AB, then there is at least one point in C, point C in AB, such that f of B minus f of A all over B minus A equals f prime of C. So let's decipher that. So we need a function that is continuous on a closed interval and differentiable on that same interval. Okay, So in this case, this doesn't tell us that f of a has to be equal to f of b. It doesn't restrict us. But we do need to draw some function in between here. I could draw a straight line in between there. I could draw just a curve in between there. I could draw something that was super wild and crazy in there, as long as it's continuous and differentiable. All right, so no sharp points, and no vertical tangent lines, and no holes or breaks in the graph. So I'm going to be kind of tame again, do something that looks like that. Okay, but really you could draw anything that's continuous and differentiable in between those two. It will work for any curve that meets those qualifications. So this says there's at least one point C in the interval AB. So again, we're looking at an x value in that interval, such that f of b minus f of a, f of b minus f of a would be that distance, over b minus a would be that distance, is equal to f prime of c. Well, f of b minus f of a, y2 minus y1 over x2 minus x1, is the slope of the tangent, or not tangent line, the slope of the secant line between those endpoints. So f of b minus f of a over b minus a is the slope of the secant line. Okay, and it says there's at least one point in C where the instantaneous slope, all right, the derivative is equal to that slope between the endpoints. And so we can take our paper again and we can slide it with that slope. We can slide it up or down. Let's start with down. Slide it until about right there. That seems to have about the same slope. So I'm going to estimate about right there. And I could slide the other direction. Let's see where we're going to get that slope, maybe about right there. Again, this one has two, but there could be many. There could just be one. But the mean value theorem says there exists at least one. So at those two places, C1 and C2, the slope of the tangent line there is equal to the slope of the secant line between those 2 points, between the endpoints. We're going to do a couple examples using the mean value theorem and applying it to just some equations without an application. And then we'll do some application problems also. Let's look at problem 21. F of x equals 7 minus x squared on the interval -1, 2. So to determine whether the mean value theorem applies to the following function, we go back to the mean value theorem. And we need it to be continuous on the closed interval. So what we're checking for, is there any place between -1 and 2 that we can't put into this function 7 minus x squared, that we would get something that gives us a hole, an asymptote, a vertical asymptote, or a break in the graph. So no, we can put every value between -1 and 2 into this function and there's no problem. So check, it's continuous. Differentiable, we do the same thing with the derivative. F prime of x is equal to, I have to take the derivative of this. The derivative of that is -2x. And there isn't any value of x that I could put in here that causes a problem. So it's differentiable on that interval. For right now, I'm not going to have you worry too much about the closed and open pieces of this. They need to be there, but I'm not going to have you worry about it. All right, so then the mean value theorem says f of b minus f of a. So our a and b are -1 and 2. So I need f of 2 minus f of -1 all over b minus a, which would be 2 minus -1. And that's going to be equal to the derivative evaluated at c. So the derivative evaluated at c is -2c. In some books, they'll put a c here. In some books, they don't care and they just put an x here. because c is an x value. So if you want to put an x value in there because that makes more sense to you, or you're following the book and they put an x value in there, that's fine. I'm accustomed to putting a c value in there. So we continue, we figure out what f of 2 is, we figure out what f of negative 1 is. So we evaluate that, we get 3 minus 6, 2 minus negative 1 is 3. It's still equal to negative 2c. 3 minus 6 is negative 3. Negative 3 divided by positive 3 is negative 1. Negative 1 is equal to negative 2c. And so if we divide by negative 2, we get c is equal to 1/2. So let's look and see what that means graphically. So here's my function, 7 minus x squared, on the interval from negative 1 to 2. And here's that secant line between the endpoints that's connecting the endpoints of that graph on that interval. And the slope of that secant line is negative 1. If you look at it, it goes down 1 over 1, down 1 over 1. So the slope of that secant line is negative 1. And then we would slide, if we could take our paper, we would slide it up until we hit a point on here that has the same slope. And so we found that that occurs at an x value, or c, equal to 1/2. So here's 1. If I go over to 1/2 and go up to my curve, right there, that slope is the same as the slope between the endpoints. And that's what the mean value theorem is guaranteeing, that there will be at least one point, if it meets the qualifications, that there will be at least one value of c or x that gives you the same slope. The instantaneous slope is the same as the average between the endpoints. I want to look at 24 quickly. F of x is equal to 1 over x minus 1, the quantity squared, on the interval from 0 to 2. And we're to determine first if the mean value theorem applies. And so the first rule is that it has to be continuous on that interval. So continuity means that there can't be any value of x that I put in here that causes a problem. And so in this case, if I put in x equals 1, 1 over 1 minus 1 squared is 1 over 0. That causes a problem. So because that's not continuous on this interval, the mean value theorem does not apply, and we don't continue. So let's look at what that means. So here's a graph of 1 over x minus 1, the quantity squared, on the interval from 0 to 2. If I connect the endpoints on that interval, that would have a slope of 0. But notice, nowhere on this graph do we have a slope of 0. There's a vertical asymptote there. There's no place that I could slide my paper up and have a slope of 0. So the mean value theorem doesn't apply on this interval. However, if I changed the interval, maybe I changed it from 0 to 2 to 2 to 3, then the mean value theorem would apply on that interval because there's not any problems in that interval. So you have to look at the interval. You can't just say, okay, this at 1, this isn't continuous, so the mean value theorem doesn't apply. That doesn't work. All right, you have to look at the interval. It applies on this interval because everywhere in that interval it's continuous and differentiable. Let's look at problem 27. F of x equals sine x on the interval from negative pi over 2 to pi over 2. So we need to check, is it continuous and is it differentiable? So continuous, sine of x is continuous. There's no holes or asymptotes or anything weird happening in here. Right, and it is differentiable. If I take the derivative of this, I get f prime of x equals cosine of x, and that's also works on this interval. So sine of x is continuous and differentiable, so check, we can use the mean value theorem. So then f of b, here's your a and your b, a and b, and we say f of b minus f of a all over b minus a is equal to cosine. Again, I use c because I'm accustomed to that, but your book might use x. Either way, c represents an x value, x represents an x value, that's fine. So then we put pi over 2 into our function, sine of pi over 2 minus sine of negative pi over 2 over pi over 2 minus negative pi over 2 equals cosine of c. Sine of pi over 2 is 1, Sine of negative pi over 2 is negative 1, so we get 1 plus 1 is 2 over pi equals cosine of c. And now we have to solve for c. You can type into your calculator the inverse cosine of 2 over pi, but you need to be careful, and I would suggest that you look at this graphically, because if I look at this graph, here's my graph of sine of x on that interval, and there's the secant line between those two endpoints on that interval, and we're trying to find at least one point on that curve that has the same instantaneous rate of change as it's the same as the average rate of change between the endpoints, or the slope of the tangent line is the same as the slope of the secant line. Well, if I look at this, if I would slide this line back and forth, I'm going to get a point over here somewhere, but I'm also going to get a point over here somewhere. So if I type inverse cosine of 2 over pi into your calculator or into Desmos, remember arc cosine and inverse cosine, cosine to the negative 1, are the same thing. If I put this into Desmos or put it into my calculator, I'm going to get one value. I get that value of 0.88 and so on. So I look at this and I see, well, that's true over here, but you can use symmetry and you can say, well, that's going to happen also at the negative 0.88, so on. All right, so that's one way that you can do it. You could also, and let's look at that really quickly. Let's see one of those. So this slope between the endpoints is the same as the slope at that point, 0.881, right? Just rounded. Okay, I could write in the other equation and put in that tangent line and get the other point in there. And then the other thing that I could do, if I don't notice that there's symmetry there, I can, and I want to solve this equation, when is cosine of c or cosine of x equal to 2 over pi? The other thing I can do is I can take all this stuff off, and I can graph cosine of x, and I can graph 2 over pi, and I can find where those two things intersect. And I can see on this interval from negative pi over 2 to pi over 2 that this is going to intersect twice. It intersects there, and it intersects there. And so you're going to get both of those places if you want to solve it that way. But just make sure that you are checking with the graph that you get all of the values, because if you just type that into your calculator, you're just going to get one value. We get two more theorems from the mean value theorem, and I'll let you go through the proofs of those theorems on your own if you're interested. They're in your book. They're not too difficult to read through. And one theorem that we get is if f is differentiable and f prime of x is equal to 0 at all points of an open interval, then f is a constant function on that interval. And so the only way that we're going to have a derivative equal to 0 for all points is that the function has to be a horizontal line or a horizontal segment on that interval. The other result that we get is that functions with equal derivatives differ by a constant. So if two functions have the property that f prime of x is equal to g prime of x, their derivatives are equal to each other, then they differ by a constant. So one of the functions, f of x, has to be equal to a constant plus or minus g of x, right? Or we can write it like this. F of x minus g of x equals a constant. The constant could be positive or negative. We could solve for f of x and say f of x equals g of x plus a constant, right? Or we could say g of x is equal to f of x minus the constant, depending on what the constant is. And so anytime that the derivatives are equal to each other, that means that the functions differ by a constant. So let's think about that graphically for a minute. I have some functions here that their derivatives are all equal to 2x. F prime of x is equal to 2x, g prime of x is equal to 2x, h prime of x is equal to 2x. And so let's say we look at x equals 1. So here's x equals 1 on the red function, right? That slope there is equal to that slope on the black function is equal to that slope on the blue function. And all of these just differ by a constant. And what that theorem's saying is that if the derivatives are equal, the two functions have to only differ by a constant. And I could put any constant here on the end, positive or negative, and that those derivatives would be equal, which would mean the slope would be the same at each x value. And so this is just a vertical shift up or down. Let's look at a couple more problems that you're going to get out of this section. Explain why or why not, determine whether the following statements are true, and give an explanation or counterexample. So these are all kind of different from each other. The continuous function f of x equals 1 minus the absolute value of x satisfies the conditions of the mean value theorem on the interval from -1 to 1. And so what I would do is I would graph that. And if I graph that, I see right away that there's a sharp point between -1 and 1. There's a sharp point, and so that's not differentiable on that interval, and so the mean value theorem does not apply. So that is false. B, two differentiable functions that differ by a constant always have the same derivative. That is true. If two functions differ by a constant, they're just a vertical shift up or down. The derivative of the constant, when it's added or subtracted off the end of a function, the derivative of that constant piece is 0. So those two derivatives are going to be equal to each other. And C, if f prime of x is equal to 0, then f of x is equal to 10. That is false. F of x can be equal to any constant. I could say f of x is equal to 20. The derivative of 20 is 0. So C is false. Number 36, without evaluating derivatives, determine which of the functions have the same derivatives. And so this is going to depend on some of our log rules, and since we didn't do Unit 1, that was developed some of this kind of pre-calculus stuff, you may not remember your log rules. So let's look at those and simplify these or rewrite them in different forms. They may not look simpler, but we can rewrite them. So g of x is equal to the natural log of 2x. Log rules say that this is the same as the natural log of 2 plus the natural log of x. So multiplication you can split into the addition of two logs. H of x is equal to natural log of x squared. Log rules say you can bring that 2 in front, so we get 2 times the natural log of x. And p of x is equal to natural log of 10 x squared. And so we can say that's equal to, we can do both rules, natural log of 10 plus the natural log of x squared. And that equals the natural log of 10 plus 2 times the natural log of x. And so we used both rules there. And now we want to know which of these derivatives would be the same. And we could go through and take the derivative of each one of these and say, okay, those derivatives are the same, but that's not what they're getting at. They want you to look at the functions and determine which ones have the same derivatives. So natural log of x, it can't be rewritten in any other form. Natural log of x, we could take its derivative. All right, and then I notice that g of x is equal to the natural log of 2 plus the natural log of x. But natural log of 2 is just a constant, just a number. And so the derivative of the natural log of 2 is 0. And so these two derivatives would be the same thing because they differ by only a constant. So without taking the derivatives, we know f prime of x is equal to g prime of x. Similarly, h of x we rewrote as 2 natural log of x. That's not going to be the same as these up here because this is a constant multiplied by the function. When they say they differ by a constant, it either has to be added or subtracted from the functions for the derivatives to be the same. If you have a constant multiple, that constant multiple is going to change the derivative, so this derivative is not the same as either of these. But if I come down here, when I rewrote this, this is now just a constant, and these two functions differ by only a constant, and so their derivatives are equal. H prime of x is equal to p prime of x. There are many application problems in this section, and this is just one of them. Avalanche forecasting. Avalanche forecasters measure the temperature gradient dt dh, the change in temperature with the change in depth, which is the rate at which the temperature in a snowpack T changes with respect to its depth. A large temperature gradient may lead to a weak layer in the snowpack. When these weak layers collapse, avalanches occur. Avalanche forecasters use the following rule of thumb. If dt dh exceeds 10 degrees Celsius per meter anywhere in the snowpack, conditions are favorable for weak layer formation and the risk of an avalanche increases. Assume the temperature function is continuous and differentiable. Given that situation, let's look at a couple problems with that. An avalanche forecaster digs a snow pit and takes 2 temperature measurements. At the surface, h equals 0, the temperature is negative 16 degrees Celsius. At a depth of 1.1 meters, the temperature is negative 2 degrees Celsius. Using the mean value theorem, what can he conclude about the temperature gradient? Is the formation of a weak layer likely? And so in these problems, you are looking to find 2 data points. And we want to know if dt dh is, will ever get to 10 degrees Celsius per meter. And so I want to find 2 data points of h and t. And so they've given me that information. At h equals 0, the temperature is negative 16. And at h equals 1.1, the temperature is negative 2. So there's our 2 data points. And we're going to find the slope between those 2 points. So negative 2 minus negative 16 over 1.1 minus 0 is 14 over 1.1, which is approximately 12.7 degrees per meter. So the mean value theorem tells us that because the slope between those 2 points is equal to 12.7, that there has to be somewhere within that region between 0 and 1.1 where the temperature gradient has to reach 12.7 degrees per meter. So knowing that 10 degrees Celsius per meter is that cutoff for the temperature gradient creating a weak layer, we can say yes, the formation of a weak layer is likely because this is greater than 10 degrees Celsius per meter. As opposed to part B, where we do the same calculation, we get 7.86 degrees Celsius per meter. Now, what the mean value theorem tells us is that there has to be a point where that gradient reaches 7.86, right? But it doesn't tell us that there has to be a point that it reaches 10. And so this is tricky. You might say that, well, there's definitely not a place where it reaches where it reaches 10 degrees Celsius per meter. But you can't really say that because the mean value theorem doesn't tell you that it doesn't reach 10 degrees Celsius per meter. It just tells you that it has to reach this 7.86 degrees Celsius per meter. And so your book says, while it's still possible that the temperature gradient exceeds 10 degrees Celsius per meter somewhere in the snowpack, one may suspect that the formation of a weak layer is not likely in this case. And so that one's a little bit trickier. Let's look at 2 more problems with that. Because snow is an excellent insulator, the temperature of snow-covered ground is near 0 degrees Celsius. Furthermore, the surface temperature of snow in a particular area does not vary much from one location to the next. Explain why a weak layer is more likely to form in places where the snowpack is not too deep. And so let's look at those. So the temperature gradient is let's think of it as a change in temperature over the change in depth. So if I look at this fraction, let's do this for C and D, all right? If I look at this fraction, the way the temperature gradient gets bigger is either the change in temperature gets greater or the change in depth gets smaller. The way a fraction is going to get bigger is if the numerator is bigger or the denominator gets smaller. And so this says, explain why a weak layer is more likely to form in places where the snowpack is not too deep. So if the change in depth is small, then that's going to make this fraction bigger, which makes it more likely to have a weak layer, makes this more likely to be a bigger number and be bigger than 10 degrees Celsius per meter. The term isothermal is used to describe the situation where all layers of the snowpack are the same temperature, typically near the freezing point. Is a weak layer likely to form in isothermal snow? Explain. So this is telling us that the temperature is near zero. The change in temperature is near zero because those layers all have the same temperature. And so this is getting very, very small, and a fraction will become small when the numerator becomes small or the denominator becomes large. So in this case, the numerator is becoming very, very small, or zero, which means that the weak layer is not very likely. So that's the end of this section, and there is our practice.